Hello. For those who haven't met me before, I will repeat some of the slides from this morning, but not all of them. A few years ago, I met somebody from NASA, and we were actually talking about some ambitious missions from NASA, and I joked to him and said, look, if you keep looking for extraterrestrial intelligence, don't you think it would be better to look for terrestrial intelligence first? And I wasn't making a joke, because what I show you now is actually an exploiting of terrestrial technology for space applications, not what you normally do. If you go for ambitious long space missions, you actually have to think about hybrid propulsion technologies. You need a combination of chemical propulsion and electric propulsion for long-range missions. You look at this very old image from a solar cell. It's a crystalline silicon solar cell from the 1960s. And at that time, one of the biggest damage issues was debris from impact that could damage this cell catastrophically. So a complete failure of the electric propulsion system. Now, for that reason, most of the cells were designed to be as small as possible. And how do you design a cell as small as possible? You go for highest efficiency, and that restricts the choice of materials to gallium arsenide, which is the leading material of choice today, and it's very close to the physical limit of operation. What I propose is actually to remove this design figure of merit and to go for watt per kilogram, which is a difference figure of merit. That opens the design space, and you pay a penalty, and the penalty is the size of the module. But if there's one thing not missing up there, it's space, because it's called space by definition. So if you have a bigger area of the array, that alone is not a specific problem. Look at this example from my technology partner in the US. Nexolve in the US is my technology joint venture partner, is the leading supplier of polyamides, which are rated by NASA to be space durable for 20 years. And they can actually be spin coated on a glass substrate to form a 6 to 7 micrometer thin polyamide foil, which is space resistant. This image up here is a solar cell, which is deployable and has a total weight and deployment of only 35 kilograms and has an area of 400 square meters. Here in this image, it's coated by aluminum. If you use the thin film technology from CSEM and EPFL, this is adding only 0.3 micrometers in thickness and no weight. But you get a 50 kilowatt AM0 photovoltaic power array at the same weight. Look at the small table below. A recently published ESA invitation to tender for advanced high power photovoltaic arrays asked for 200 watts per kilogram and 60 kilowatt per meter cube stowing volume. I can easily surpass this with this concept by almost an order of magnitude. To make sure I'm not just joking, actually I used a recent NASA publication about a planned Mars mission. And actually they are referring to commercial off-the-shelf photovoltaic gallium arsenide arrays at 212 kilowatt power. And I used the same figures of merit to compare what I could achieve with this technology. And I arrived at a net mass saving for only one space mission of up to 4 metric tons. So for the same price, you can add 4 additional metric tons of payload. And considering the normal cost of space launch, this would have a commercial value of approximately $70 million just for one launch. This is my joint venture. It's actually a combination of mature technology partners in Switzerland and in the US. And to be more concrete, Nexolve is the only company in the world actually providing space-rated polyamides by NASA. And this material is subject to ITAR, International Trade in Arms. And that means it's very hard to get access. I negotiated access also to the R&D lab of Nexolve in the US to develop these products together. This is CSM in Switzerland, the leading infrastructure for thin film PV since the 1980s. And then the picture on the bottom, you see an amorphous silicon single cell on polyamides coated directly and actually space qualified and qualified in PV current voltage characteristics, published in the paper several years ago. The roadmap, of course, requires some funding for the serial interconnection of these cells into a power array. And this is a technology from terrestrial applications. The coating process is the same used to create thin film LCD screens, for example, for this television. It contains the same production equipment. That is a mature technology. With this technology, you can actually increase the watt per kilogram almost an order of magnitude. For every long-range mission, this is, I think, the only way to move forward. any other technology has reached its design limit. These are the contact partners, and I'm currently looking for funding to get started with the next TRL for serial interconnection. Thank you for your attention.
How much funding are you looking for? What will you be able to achieve with that
These
funding?
are two questions. Thank you. It depends how far we want to go. We have actually a high TRL on the substrates. We have a high TRL on the single cell, which has flown in space by NASA. The combination is a low TRL 3, which is quite low, I agree. So what we need is, I would say, proof of concept funding of around €1 million to go to a serial interconnected array which can be flown in space to demonstrate its viability for actually power generation. With less than that, I'm afraid we may get stuck in the middle somewhere. So I think it's a technology for large-scale operations. It's not easy to go for niche applications with this because there you compete with gallium arsenide, which is available on the market, which is quite expensive, but it works. So actually I'm competing with established technology for small products. But for large missions, nothing can beat this technology. So if you really want to go to Mars, in my view, you have to go this way. Otherwise, you just have penalties on the weight of the payload. But that's a long-term plan. Short-term, I think about $1 million. That's what we currently look for.